Hi everyone. Today we'll be talking about the new recent paper called I-Jepa, which is a continuation of ideas presented by Jan LeCun in the paper called A Path Towards Autonomous Machine Intelligence, where he lay out an idea how to build more human-like intelligence. Here is a sketch from this paper. He laid ideas how to make all these modules except from the configurator and the Joint Embedding Predictive Architecture. He thought it could be a world model. So this actor could have something more reliable to have predict and not to come up with some not true information. So what is this I-Jepa Joint Embedding Predictive Architecture? It is a self-supervised method that is non-generative, non-contrastive, and non-probabilistic. And why is that? Why don't we after want to use prediction or regression tax? Well, it doesn't have some mode collapse or other issues, but we, for the same x value, may have several y values for several different predictions that are completely plausible. And if we just predict one value, regress this value, we may have a blurred prediction which may not be true. And what about gentile latent variable architecture? This can collapse, so the information from X will not be used, for example, by predictor, and only variation in this latent variable Z will be used to generate the Y. And what about autoencoder? It is also can collapse by learning the identity function, and also may suffer from mode collapse. And if we can use joint embedding architecture, it also can collapse, for example, by learning to predict only some constant value for any output, or just be same over the broad region of the output space. Sure, this issues was tackled in different papers, but authors think that it may not be enough, and we need something even better. So what here below is a sketch for I-Jepa. So here, what do? We have the x and y values. We encode that both this could be different encoders, and we have this prediction. So we from x predict encoded value of y. Why? Because if we try to reconstruct y as it is, it may have some not needed for us information. For example, if we want to get information from the scene, we don't need to know exact value for each leaf or some other object. So we could so this encoder can filter out these details and leave only valuable semantic information. And Z may be used to variate over several possible. This latent variable Z may be used to variate over several plausible y values. So we, for example, don't know what we may have several solutions for this x, and we can variate to get the variate z to get other y. And how it could build on practice. For example, we can, for encoder, this is from VCrack paper losses. For example, what we can do so for encoder x, we can try to maximize information content. For example, we can force covariance matrix to be an identity matrix, and the same one should be for maybe the goal for the encoder of y. A prediction error, it's maybe simple L2, L1 losses, and also we want to minimize information content with some regularizer function. And why don't we want to use contrastive samples? It's because he is afraid that it won't work well in the with high dimensionality vectors. For example, if we have some function like this, when we want to make it more correct with contrastive sample, we need them many and to be in the exact position to adjust this initial function. But with regularizer, we can try to push this initial function as close to the initial points as we can. And also so this will be a function from both y and x. And we have from the same x, can have several y's. So it won't, we can find the several y's then. And how it was implemented in this, how this idea was implemented in this I-Jepa paper is that works on the images. So basically, we have some context and a target. Target is basically the whole. Basically, it's context is visible part. Target is not visible part. Context encoder is width transformer. Predictor also width transformer. Well, and target encoder it's exponential averager over counter recorded values. So what we do, we take, given the context, and encoding this mask information and give it to the predictor with the tokens of the targets that we want to predict. So this one patch, this one, and this one patch. We predict them with these values with the predictor, and then we compare results with this results from the target encoder, which produced which takes to the input the whole image the whole target image, and we just look at the necessary tokens and compare them. As loss is use simple L2 loss without some additions. So this is an example of what we may get to at the input. What authors do, they have an image, they sample 4 target blocks with the scale in the range from 1/6 to 1/5 of the whole image size. Aspect ratio is from 0.75 and 1.5. So it won't be some crazy rectangle. And also to sample context blocks can be a whole image or just 0.85 of the whole image. And if some target exceeds this value, it just will be masked out. So we just may ignore some small part of the initial image. And what about results? And we will be comparing it to this several models. And this highlighted in yellow, these quite similar. So they don't use some, meaning that they don't use augmentations to generate positive pairs. They just use masks. So yeah, well, what about the results? This is the results on ImageNet 1K with linear probing. It has, well, the largest I-Jepa encoder that was trained and with the high resolution has the best results between the methods without the view data augmentations. But I-Bot method with extra view data augmentation has basically the same accuracy, and actually there was a Dino version 2 which has the even larger accuracy. but it also can be tried pretty fast compared to this other methods without view data augmentations, and even comparing to the data that use indeed additional data augmentation. By these augmentations, I mean just random cropping, color, messing with color, flipping, and stuff like that. Also, they tested linear probing using only 1% of the examples for each class, and it also had pretty good results with a larger model having the best score between the models that were used in that they tested. And also they tested on the dataset that the model wasn't trained on. And here we also have good results when taking the methods without data augmentation, but methods that use these augmentations like I-Bot have even greater results. See for Stoy, 100 is a dataset of small images places, 205 is dataset from where basically for classification, but where there's more about the scene and not the object in the center. And naturalist is also classification dataset for nature of things like plants, animals, and stuff like that. And Clever is the dataset is the generated dataset for visual question answering. So there are some random objects like cube, triangle, prism, or something like that, and questions about their layout, about their quantity, and stuff like that. So they tested also on this dataset, having not bad results, but it's still not the best ones. But given that the model can be trained with faster than these previous models, it's really efficient when counting GPU hours. Yeah, so they also presented a lot of ablation studies. For example, they tested different strategies for generating masks. Multi-block is the strategy that I told, so we just find random blocks with this size for targets and block with this size for context. Rasterize means so just image is split to 4 equal quadrants, and from one quadrant is our context and 3 quadrants is our targets, and we try to predict from this one quadrant other 3 quadrants. Block is we just create this random block with this size, and context is complement to this our target. Random is basically the same, but we just randomize. They take random patches. Also, they tested predicting in this embedding values, and also tried to predict directly pixel values. And indeed, it took they trained it for much longer, and the results weren't as good. Also, they tested using different target scales and context scales to select the best ones. Here they search best context scale, and here they search for the best target scale. And also they looked at the predictor depth and predictor width, but the tested presented only 2 different values. So we are trying to encode this information, and you would like to test what model actually encodes. So they took a method called RCDM, which means representation conditional diffusion model. So they basically trained a diffusion model with that was additionally passed this encoding from this for this target, for this particular target, and generated results with different seeds. And here's what's model generated from this from embedding. So it basically knows a little bit what's about the scene, but it doesn't know the particular structure. It can be seen as this image of lemons or of the clock. So it knows it's something like clock, but it doesn't know which particular clock is it. So it can encode semantic information, but since we don't predict pixel values, it won't give us this accurate result. Also, they tested with the same method to completely. Well, they took uh, all encodings outputted from the target network, averaged them, and also generated the images with this joint diffusion method. So here's in the first column are originals, and all others it was model generated. So in conclusion, this is another self-supervised learning method. It's supposed to be more efficient and has generalization on par with the methods that use extra view data augmentation. And yeah, I guess it's all for now.